Okay, in your page 217, electricity, just summarize what we are going to cover. 9.1 electric current, 9.2 potential difference and power, 9.3 resistance and resistivity. That's our definition. Rate of flow of charge for electric current, or summarized by the formula. Then define charge and Coulomb. Find PD. That's our definition for PD. And derive this equation. Power equals to current times potential difference. So this alternative formula. And define resistance and ohm. That's our definition for resistance. And look at various graphs, current versus potential difference graph for various component, metallic, conductor, lamp, semiconductor, diode. And then we study finally for this topic, resistivity. There's the formula for resistivity. And the new for your syllabus is sensing devices. Okay, that's your syllabus. Always go to your data and formula, see what is given. Right? Like elementary charge, E is given. Electric current, the formula A and VQ given. Okay. For topic 10, practical circuits or sources of EMF. We have a circuit there. Right? Usually you will give a circuit diagram lah. That's the lamp. That's the lamp. That's the emitter. That's the emitter. There's a switch. There's a switch there. So you're supposed to be able to read the circuit diagram and then connect it up. So we are going to look at 9.1 electric current, and there's your lamp, potential difference and power or energy dissipated by the lamp. And then we are going to look at resistance and resistivity of the lamp.
Sure.
Yeah.
What's the difference between resistivity and resistance?
Resistivity is the, let me just go back to, we will define it anyway lah. Resistivity, that one. Okay, resistance is defined as potential difference over current. That's a resistivity. We look at the resistance. Resistivity is basically the resistance of a unit length and unit cross-section area. Anyway, we look at it. Don't go too far yet. Okay. Electric field used to be AS, but now they are transferred to A2. But just let me go over with you roughly lah, so that you have some idea. You won't be tested lah. Electric field is defined as a force per unit positive charge. That means force acting on a unit charge, unit positive charge. Direction is the force on the positive charge. Direction of the electric field, just like gravitational field, is always downwards onto the Earth's surface. This is the direction where the object will move. Positive charge will move in direction of electric field lines. Okay, motion of charge particle. You have a positive charge, right? We call it Q. It experiences a force. A stationary proton accelerates in the direction of the electric field or move from negative potential to positive potential. An electron accelerates in the direction opposite the electric field. Right? That direction electric field. The positive charge move in the direction of the electric field. Electron move in the opposite direction. Motion of charged particle. An electron moving in the direction of electric field decelerates to rest. So if that electron is moving in the direction of the electric field, right? Remember the force is opposite to the electron, opposite to the direction of the motion. So the electron will decelerate to a stop and then reverse direction and accelerate in the reverse direction. Then we come to conductor and insulator. How do we know it's a conductor? Right? Where the electric current will flow, there's a battery, there's a bulb. So we can show that by connecting the paper clip or steel to the terminal, the light will light up. Whereas insulator, current doesn't flow through other materials. These materials are insulators. So we join the insulator to the wire, not current. So plastic and insulator. Okay, what's the difference between conductor and insulator? Conductor, electric current can flow freely. Insulator, electric current cannot flow. Why is there a difference? Example of conductor will be copper, mainly metal. Most non-metal solids having extremely high resistance to the flow of charge to them.
Yeah.
Yeah,
Is there a non-metallic that is a conductor?
carbon.
Carbon?
Carbon is the only one that conduct electricity. Graphite
Oh,
most of it
okay.
are insulator doesn't conduct electricity. Only graphite is the exception.
Plastic, yeah?
Plastic cannot conduct electricity. Plastic are
Oh,
all insulator. What is the difference? Different
the
is, yeah,
wood can, right?
say
Wood,
again,
wood.
wood cannot. Wood are insulator.
Then why would I stand at the tree, then like the lightning will pass through one?
That's a sharp point. Usually, you are the sharp point. Your body, you may have a conductor in your body, like
Oh,
a belt or metal somewhere in your body.
how the electricity flow from the tree?
Not from a tree, it's from the lightning.
The lightning to the tree, then to your body,
Lightning strike you.
Oh,
That's why in a rainy day, you should not go under a tree.
okay.
Okay, so what's the difference between conductor and insulator? Outer electrons of the atoms are loosely bound and free to move through the material. It just apply electric field, then the electron is removed and free to move. Whereas insulator, no free electron. Electrons are held tightly by the atoms or by the nucleus. Conductor, when no current is flowing, these free electrons move randomly throughout the structure. Typical speed is quite high, 10 to the power 6 meter per second. That's how the electron is moving at random in the conductor. This is a simple circuit, a battery and a wire. Positive terminal is high potential, negative terminal is low potential. Usually we don't connect this way. Why? Why don't we connect a wire to a battery like that? Any reason? The wire will heat up, become very hot after a while, right? So if it's made of insulate, if there's an insulator, the insulator will melt. Okay, we have a battery or voltage source. Maintain a potential difference, high potential, low potential across the wire. This voltage establish an electric current. We have positive terminal, negative terminal. Then from the positive terminal to negative terminal, there will be electric field. There will be a force on a positive charge. So that's electric field. The electric field points in the direction of the decreasing potential, high potential to low potential. That's where the electric field will go, and drives conventional current through the wire from positive terminal to negative terminal. The conventional current is the positive charge. We just imagine the positive charge can move lah, but actually the positive charge doesn't move. It's just like conventional because you have decided by scientists. That's how they initially thought it was the positive charge that moved, but later they realized it's the electron.
Oh, so high potential is positive one.
High potential, positive terminal,
Oh, okay.
then electron will move from low potential to high potential or accelerates in the opposite direction. Okay, conduction in metal. You have the positive ion, right? Metallic ion, and then these are free electron. Free electron move at random. Right? It's just like the air in the room move at random. In the absence of electric field, there is no net motion. No net motion, it's just random and then come back to almost the origin after some time. Resultant attractive force will prevent the electron from leaving the conductor. So we ask why electron cannot escape. Now we look at the electron. There is a attraction from the positive charge, nearby positive charge there. I remember there are a lot of positive ions there. So I'll show you some example. There's the attractive force. So this attractive force, there's a resultant attractive force to pull the electron from leaving the surface. Positive ions vibrate about fixed point. They don't move, but they vibrate about fixed point. Right, so you connect to a battery. This is positive terminal of the cell. This is negative terminal of the cell. Then what would happen? Right, the free electron, that's your electric field. Right, always from positive to negative. Electrons accelerate in opposite direction. Right? This free electron will accelerate in opposite direction. What will happen? Right, remember this positive charge is vibrating. So this electron, as it moves at, remember it's moving at random, but it's also being accelerated. So it's going to collide with the positive ions, give energy, lose its kinetic energy. That's why we have to keep on giving it energy to make it go forward. Whereas the positive ions receive kinetic energy from the colliding electron. So it receives kinetic energy, it will show as it vibrate faster. Increased kinetic energy appear as heating effect on the metal and increase in resistance opposition to motion. So two things happening. When the electron collide with the vibrating positive ion, it gives kinetic energy to the positive ion. Positive ion vibrate faster. So it's going to collide with more electron. So what are the effect? Effect will be one, when we touch the metal, it feel warm. Two, right, we lose energy. So there's some sort of like a resistance to the flow of electron. That's where the idea of resistance come in. So the conventional current is the flow of positive charge. That conduction in metal, without electric field, that's how it will move. Right? Start and finish almost at the same point. This is called random walk. In absolute electric field, there's no net motion. The haphazard path is due to collision with positive ion. Right? collide with positive ion, deflected, collide with positive ion, deflected, collide with positive ion, deflected, until it come back to, after some time, it will come back to almost the same point. Where there's an electric field, the electron, right, it starts, but it has a direction. No doubt it is moving at random also, but it is moving forward, right? That means moving against the electric field lah. So we will observe two things. One is Joule heating. Application of PD across a conductor will produce an electric field in the conductor. Free electrons accelerate towards the positive terminal of the cell. Average drift velocity of electron is about 10 to the power minus 3 meter per second, about 1 millimeter lah. So it's very slow lah. But remember, right, velocity is a vector. There's your random velocity, there's the drift velocity, so the two will add up as a vector. An electron flow in a conductor, they collide with the vibrating atom. Energy is imparted to the atom. We are just repeating. Positive ions is vibrating, the electron is colliding with the positive ion. So we see the energy transferred to the positive ion as temperature of the conductor rises. So when temperature rises, we see the amplitude of vibration of lattice atoms increases. The positive ions vibrate with larger amplitude. Cell provides, right? The electron is going to lose energy to the positive ion. So we have to give it more energy. So the cell provides energy to maintain a constant current. Electrical resistance of conductor is simply a measure of the potential difference required to maintain the current. Right? So we have to use energy there. Potential difference is the energy added to the positive, to the moving positive charge to make it constant current. Thus, both the heating effect of the current and the electric resistance are a result of electron colliding with the lattice. Right? So the heating effect and electrical resistance are due to the collision of electron with the positive ions. Right? Charge carrier. The others we are not interested lah. Right? Metal, example sodium, charge carrier is electron. Gas and electrolyte, example copper sulfate, to be positive and negative ions. Semiconductor we are interested, silicon and germanium example, we have electron and hole. These are the charge carrier. Okay, define potential difference, current and resistance. What is current? How to calculate energy to move charge? How to calculate resistance?
Teacher,
Yeah,
all these questions, right? Can I like let's say what is current? I use the V equals IR formula and I derive it. Can or not?
cannot. Current you must is specific. Right? Is specific. Electric current is the rate at which charge flow through a cross-sectional section of a conductor. Specific already. How we define current? Rate of flow of positive charge. Okay,
Oh,
that's electric current. Memorize definition.
I cannot say oh, okay.
Each resistance and potential difference is defined differently. So you cannot use the other formula to define current. Current is defined separately. It's the rate at which charge flow through a cross section of a conductor. Or for steady current, we can write as electric current equals to quantity of charge divided by time. Okay, in terms of formula, Q over I or dQ dt. Charge is measured in coulomb, time in second. So remember, it's a ratio. Remember, it's a rate, not a ratio. Alright, so the unit of current is Coulomb per
Okay.
second, or we call it ampere lah. Capital A, to honor the scientists who do research in this area lah. Electric current in copper wire. For electric current in copper wire, the charge carrier are mobile electron, electron that move, and the positive charge copper ions are essentially stationary in the metal lattice, not actually stationary lah, by vibrating lah. Fixed in position, that's what I mean by stationary, but vibrating. Electron is the one that moves. Nevertheless, treatment of electric circuit usually use conventional current, as if positive charges are moving. So normally we use conventional current because that is how scientists first thought that it was the positive charge that moved. So rather than change it, they use convention. That means we agree that it's the flow of positive charge from, if we say conventional current. Right? So electric current means conventional current. What does the area under the IV, under the graph of I versus time graph represent? Any idea?
Resistant.
Go to the equation, no?
Oh, yeah.
Area is IT. So total charge, right? From the formula, I is Q over T. So IT cross multiply. IT is area, total charge during a certain time. Okay.
The answer is Q, is it?
Q, total charge, flow in the time, T. Okay, measurement of current. This one is, you can see the 5 there, so it's called full scale deflection 5 milliampere. Ammeter measures current, full scale deflection, FSD, full scale deflection, the maximum current the meter can measure. So we normally will not measure more than that lah. You will spoil the meter. Some ammeter has two scale to measure low and high current. Right? There's two scale there. Ideal ammeter has internal resistance. Normal ammeter has a low resistance. Right? Ideal ammeter has no resistance. That's what we want. But usually ammeter has low resistance. Right? Symbol for ammeter. Right? That's your circuit, simple circuit. Your cell, your switch, ammeter component. So ammeter is always in the circuit or in series with the component. Right? This component, a lamp, passing with the component passing the current. Charge and Coulomb, that's for your info. Quantity of charge, Q is a product of current passing a point in a wire and the time it passes. Basically, from definition of current, Q is IT. Coulomb is ampere second. So 1 Coulomb is defined as the quantity of electric charge flowing through a given point in a circuit when a steady current of 1 ampere flows in 1 second. That means we put 1 ampere 1 second, no? Because 1 Coulomb. 1 ampere 1 second. Okay, mechanism of conduction. Right? We are just a wire or conductor. Length L, there's a cross-sectional area A. These are electrons. The current flowing in the conductor is given by the I is NQAV. Or if it's electron, then it's NEAV. Okay, so this one you can think of a charge or electron if you like. Right? This one is given in formula sheet. What is N? Number of charge carrier per unit volume. number per unit volume. Q is the charge carrier, charge on the charge carrier. A is the cross-sectional area. V is the mean drift speed. Okay, the syllabus doesn't require to derive lah, but I thought just derive it for your sake lah. It's not, doesn't take that long lah. And one way to remember is use the word near lah. Instead of R, use V lah. Right, if you want to remember miles. Okay, volume of conductor is A times L. Number of charge carrier in the conductor, right? Number per unit volume times volume is total in the volume, total charge carrier in the volume. And total charge, number of charge carrier times Q. Q is the charge on the charge carrier. Time for the carrier to travel the conductor, L over V. If V is the average drift velocity of the carrier, L is the length. So current in the conductor is Q over I. That's your Q. That's your T. Q over T. So that's your total charge. That's L over V, L divided V. So we cancel the L, multiply by V to get rid of the V there, and multiply by V, we get our equation. Okay with that?
Sorry, what's N?
Say again.
What is N?
N is the number of charge carrier per unit volume.
Number of charge carrier, okay. V is
There,
volume. Oh, okay, I
small
mean drift
v is
speed. Okay.
mean drift speed. N is the number of carrier per unit volume. Right, make sure you photostat the note. If not, you are not going to follow.
Oh yeah, I have the notes.
Anything else you want to ask?
That's all.
Q is the charge on the charge carrier lah. Okay. Determination of charge on electron. Right? I think I'll let you read yourself here. Elementary charge usually is denoted by E or Q lah. Is the electric charge carried by a proton. Right? Positive charge carried a proton, or equivalently is the absolute value of electric charge carried by a single electron. Element charge is the fundamental physical constant. To avoid confusion, over is sign E is called elementary positive charge, and that is the value. Right? We won't go to too much decimal place. Right? Quantization, it means that you can find electron as positive or negative electron, or 2 electron, or 3 electron, but you cannot find half electron or minus 3.8 electron. Right? Elementary charge means that you cannot divide anymore. This is the smallest it can go. So when we say charged particle, it can mean electron, it can mean proton, hydrogen atom that has lost an electron. Alpha particle are helium atom that has lost 2 electrons. Or it can be particles carry a charge, example oil drop, or droplet. Oil droplet usually negatively charged. Right? This is in your data sheet. In 10 minutes time, we have to stop. Mass of electron, charge of electron, mass of proton. Right? So while you wait, remember, try the worksheet
Okay.
to reinforce the formula that I've given you so far.
You mean the one you sent?
The one that I sent to you, no?
Okay.
Memorize it. What is quantization? Charges are found in integral multiple of basic charge, n times E. N is the number of electron, 1, 2, 3, or it can be 0, integer number. E is 1.6 and 10 to the power minus 19 coulomb. Example, This is done in oil drop experiment. How to calculate the average charge? Know that this is E, this is 2E, this is E, this is 3E, this is E, this is E, this is 5E, this is E, this is also E. Right? So add all the values up, you get this one. Then number of charge, number of electron, add all the red one. Total number of charge is 16E. Then divide by 16 to get the charge on one electron. Okay.
The 25.7 is you add all together, right?
Add all the charge together.
Okay.
And remember, it's 10, each of them is 10 to the power minus 19 Coulomb. And then total number of electrons, you just add all the red one.
Oh, okay.
And the total charge divided by total number will give you the charge of the electron, one electron. Okay.
Okay.
Potential difference. Right? Since electron lose kinetic energy in collision with the positive ions in the metal, we need to provide energy for electron to continue to move. That's why we become potential different. Right? That's the syllabus. Potential different and both definition memorize. Potential different or PD or V or delta V between 2 points or across a conductor in a circuit is the energy transfer per unit charge. Energy transfer per unit charge in taking the charge from one point to the other. So it's basically the energy to take 1 Coulomb of charge from one end of the conductor to the other end of the conductor. Right? Or in formula form, V equals to WQ. 1 volt is the potential difference between 2 points where the energy transfer per Coulomb in moving electric charge from one point to the other is 1 joule. So basically, we are just saying 1 volt, 1 joule energy, 1 Coulomb of charge. That's all. Okay. Memorize. Nothing much to teach you. Okay. Okay, that's a symbol for voltmeter. That's a voltmeter. This one is analog. This one is digital. The lab should have both of them. Potential difference across a conductor. Right? Can be a lamp, can be a conductor or any resistor. So the voltmeter is connected across conductor or component is measured using a voltmeter. So you want to know the potential difference across the lamp, you put a voltmeter across it. Ammeter is in the circuit. Voltmeter is connected across or in parallel to a component. Right? The lamp is a component. An ideal voltmeter has an infinite internal resistance. That's what we want. Right? Ideal is what we want. Why? So that the current will just flow there. It doesn't draw any current. The internal resistance of an analog varies. Right? This is just for your information. Don't worry about it. Ours in the physics lab is about 5 kilo ohm. Our multimeter or multi-tester is about 200 kilo ohm. And this is a simple circuit. A load, ammeter, voltmeter, a cell. Ammeter is connected in series with a load. Voltmeter is connected in parallel to a load. Parallel to the load. Ammeter is in series with the load. Load can be a resistor, can be a lamp, or it can be a piece of wire. Okay, power. Normally, in a resistor, the current flows through it as a result of potential difference. If there's a potential difference, you are supplying energy to the charge. Energy is dissipated in the resistor when the charge flow. Right? There's collision, so energy is lost to the conductor when the charge flow. So that energy is given by W is equals to Q times V. Right? Q is the charge flowing, V is the potential difference across the conductor. Power is the rate of transfer of energy. Right? There's a formula. Energy divided by time or work divided by time. Right? W is QV, QV, and then there's your time. So Q over T is I, and then there's your V. So that's the formula that we have derived. V is IV. Right? We're just deriving all the formulas that you need to remember if you can, or derive it. Right? This one we just derive for you. V is IV. Memorize this one and memorize the resistance formula, and then you can derive the others. Right? Replace the I with V over R. So you got V squared over R. Replace the V with IR. So you get I squared R. Okay,
So got three formulas.
yep.
Okay.
That's the potential difference formula, the energy formula.
What is W again? I forgot.
W is energy or work done.
Okay.
Don't worry about the mass. Just know that if a current flow through a load where you have maintained a potential difference, as you enter, this is VA, potential difference at point A, right? Wire has no resistance, so the potential difference is constant. As it flows through, it loses energy, so that's why it's going down. Then as it comes out at a lower potential. Right? As I said, don't worry about the formula, just know how it looks like. Okay, kilowatt is not mentioned in syllabus. This is for your info. Kilowatt hour is the electrical energy supplied to a heater, kilowatt heater in 1 hour. Kilowatt hour is a unit of electrical energy used to price electricity. Right, remember we cut off at any time now. So that is the value. No need to memorize, derive it. Right, 3.6 and 10 to the power 6 joule. For heating element, rate of thermal energy dissipated in time is T. Power times time is your energy. So 1 kilowatt hour, 1 kilowatt equals 1000 watt. 1 hour is 3600 seconds. And that's how we get it.
Okay.
Okay, you can try to calculate this one. As our time
I
is
do
almost finished. Calculate this
I
one.
do the one in the WhatsApp.
So I will give you about 10 to 15 minutes, then I'll contact you.
Okay, I do the work from the WhatsApp.
On the worksheet, I'll send you.
Okay. I'll do that one, okay, from question
Okay,
one.
okay, I will stop here.